Today we're going to be completing Part B of Homework 1 for separations. And what we're going to be doing today is we are going to derive the normal equations using a geometric argument that the residual error must always be perpendicular to the vector that we're trying to estimate. And to get started here, we're going to observe classic equation for the line y equals mx plus b. Now we can take this and we can put it into a matrix form for several values of x. We can say, if we've got a column of x1, x2, x3, so on and so forth, all the way to xn, with a column of an identical size made up of ones, and we multiply it by a matrix of just our n and our b, our coefficients, we can get our matrix y's, our y1, y2, y3, and so on. Alright, now what can we do with this? Nothing quite yet. So we're going to switch gears a little bit and look at an example of a vector so we can explain the idea that we're going to get to a little bit easier. So, take a vector, let's just say it points to coordinates 3, 1. What will be your best estimate of this vector on just the x-axis? Well, logically, anyone might say 3i. Why? Because it has a 3. This has a 3 in the x. But what's the actual reasoning behind this? Well, we look at a vector like 2i, for example. It isn't as close. Why isn't it as close? What are we trying to get at here? We're looking at this distance here, and this is our error vector. Now, as you can see here, the error vector for our 3i is smaller than our one for our 2i. And why is that? Well, the vector for our 3i is perpendicular. And this is massively consequential to this equation here and what we can do with it. So let's name these matrices a little bit. Let's say this is A, our design matrix. This is C, our coefficients, and this is Y. Now to find our error, obviously we're going to say our error is going to equal y minus our A times C. And that makes sense because the y is our answer and our A times our C is our best estimate for the answer. So any difference between y and AC is going to be our error. Now what can we do with this? Well, let's look at the transpose of A, our AT. What is AT? It is our A matrix flipped on its side. So x1, x2, x3, so on and so forth to xn, and our column of ones. Now what can we do with this? We can multiply it by our error vector. And our A transpose times our error vector must equal 0 if the error is perpendicular. And that's a consequence of the dot product here, because the multiplication between a vector and a vector perpendicular to it must always be 0. Now this is extremely helpful when it comes to finding our normal equations, because now we can sub in for E our equation we found over here. We can say that A transpose times our Y minus our design matrix A times our constants equals 0. And once we multiply this out and then separate our variables to either side, we can get A transpose times Y equals A transpose times A times C. Now this right here is the normal equation. Now that we've figured out how to derive normal equations for multilinear regression, let's apply this to more of a practical equation, the Antoine equation. Which states log P equals A minus B over T plus C. Now we need to do a little doctoring in this equation to get it into a form where we can easily put it into a design matrix. To do that, we're going to call this term Y. And we're going to go ahead and multiply out this T plus C, which is going to give us Y times T plus C equals A times T plus C minus B. We go even further and multiply out these variables and isolate our yt, we can get an expression yt equals at plus ac minus b minus yc. Now we can go ahead and drop this here out and call it d, because these values are all constants, so they're not going to be changing. Meaning that d is just another constant. That'll make it a little bit easier for us to put this into a design matrix. So now what's this going to look like? It's going to be yt equals at plus d minus yc. Alright, so what kind of design matrix can we yield from this equation here? Let's start over here. T plus e minus yc. Alright, what this is going to give us for our design matrix is we're going to get a column of t's, t1, t2, all the way to tn, followed by a column of ones of the same size n, and finally we're going to get a column of minus y's because of this minus sign right here. So minus y1 minus y2 all the way to minus yn. And clearly our coefficient matrix for this is going to look like A, D, and then C to yield this equation here. Of course, this is multiplied out. We're going to get a matrix of I1, T1, T2, all the way down Y and T and. So here you can see we've got our design matrix. We've got our coefficient matrix. We've got our Y matrix. And for when we go into Colab to code this up, get us a plot, I'm going to call these variables A, M, C, M, and Y, M, all for simplicity's sake. So why don't we head over to Colab and start to do some coding.
All right, now that we've went ahead and derived our normal equations up on the board, explained how we can use them to perform multilinear regression, and then applied the normal equations also to our Antoine equation, we can go ahead and move into Python and use some actual experimental water vapor pressure values to calculate the Antoine equation constants for water using multilinear regression. And of course, I've started out by importing NumPy as NP, and then from plotly.subplots, I've imported make subplots. So we can go ahead and get started. What we're going to do first is we're going to import our raw data. So we're going to say raw TP is going to equal np.gen from text of our file here, our water vapor pressure.csv. And then our delimiter is going to be commas, as it is a comma separated value file. So now that we got that all together, we can go ahead and define our t as the first value in raw TP. So raw TP comma colon comma 0. And then we can define our y, as I set up on the board, as the log base 10 of our raw TP 1, because the 1 is the pressure values in our raw data. So that creates our two matrices of all of our temperatures and then the logs of our pressures. And moving on from here, we can go ahead and create our design matrix, which we said we would call AM up on the board. So our AM is going to be an np.c underscore, which basically just combines matrices of the same size into one bigger matrix. It's useful for us because we already have a one-line matrix for our t and our y. We're going to do np.c, and then the way we did it up on the board is that we started with our t's. So we're going to have t, and then np.ones like t, so that we get a column of ones the same size as our t. And then we're going to have our y values, and that creates our design matrix. Moving on from that, we're also going to need to create our answer matrix, as you could call it. So we can say our ym is going to equal ry times our t. Let's make sure that's all good. What is going on here? Oh, I used parentheses instead of brackets. Let's go ahead and fix that. Alrighty. Moving on from here, we can go ahead and use linear regression to solve for our constants. So we're going to say A, D, and C, as are the values that we have up on the board here, are going to equal np dot linalg dot solve, and we are going to solve for the transpose or T at M, our design matrix, and then our design matrix transpose at ym. And then from there, we're going to switch from our d back into our b variable, because that is the actual variable in the Antoine equation. So we're going to say our b is going to equal our a times our c minus our d. Now that we have our constants solved, we can go ahead and create our temperature plot and our Antoine P plot so that we can create a visual plot comparing the Antoine constants, or the temperatures and pressures based on the Antoine constants we just solved for in this np.linalg.solve, to our actual data values to see how well our equation is going to fit the actual data. To do that, we're going to say that our t plot is just going to equal np.lin space from our t min to our t max with 100 values in between. And then we can say that our Antoine P is going to equal the solution to the Antoine equation. So we can say 10 to the power of, what is it again, A minus B over T plot plus C. And that will go ahead and yield our Antoine pressure plot. So now we can go ahead and compare our actual values to the values we just guessed from linear regression to find our constants for our Antoine equation. So to do that, we are going to say our figure is going to equal make subplots. Fantastic. And do figure dot add scatter. And we are going to go ahead and enter our real values. So we're going to say our x is going to equal t. Our y is going to equal 10 to the power of our y, since we took the log back up here. And we're going to do mode equals markers, since this is data points, not a linear line like we're going to have with our Antoine derived values. And then we're going to add our theoretical values. We're going to have our x equal our t plot. Our y is going to equal our Antoine P. And this time our mode is going to be lines. Folks, I just realized I made a pretty major mistake right up here. Forgot to put a negative in front of my y, as we discussed up there. The y needs to have a negative in front of it because of the overall equation we created to make our design matrix. But other than that, I think we are going to go ahead and do figure dot update y-axis. And we're going to update that y-axis to be a log form, because as we know, the plot is going to look like an exponential unless we have the y-axis be in logarithm form. So it'll just make everything look a little bit nicer. So let's see our plot, see how it worked. Look at that. So as we can see here, that multilinear regression does a really good job of finding constants for your equations, your empirical equations like the Antoine equations, from some actual experimental data, because the line created from those constants that we found through multilinear regression match the actual data points perfectly. which is exactly what we'd like to see. I think that is the end of our homework 1 part B for separations.